Now this is something that we haven't done much in this class, but you can actually, depending on your numerical method that you're using to either solve equations or to, in this case, take the integral, you can actually find the error e between the real integral a and the integral using the trapezoidal rule with n plus 1 equally spaced points, which I'm calling a sub n. Now, it's beyond the scope of the class to talk about how this error is derived, but this error, e, which I'm going to call en, because it's using n plus 1 points, or if you have n plus 1 points, what you have actually are n subintervals. That's why it's en instead of en plus 1. So if you have n subintervals, this error between the two is, well, it's defined as the actual area minus the approximate area. And this error is equal to c over n squared, where n is your number of subintervals. And c is some bounded constant. I'm not going to tell you what the bounds are, but we don't know what this exact value of c is, but it's some c that's bounded by like the shape of your function and the number of subintervals that you have, etc. It's not infinity, and you can put bounds on it even though you don't know what it is. Now what happens if we take, instead of n plus 1 equally spaced points, we have 2n plus 1 points. In other words, we have 2n subintervals. Well, in that case, the area for 2n is equal to, defined as the true area minus area 2n, with 2n subintervals, and that's equal to some other c, which I'm going to call c prime, divided by, instead of n squared, since we have 2n subintervals, it's 2n squared, or some other constant c prime over 4n squared. Now, this is cheating a little bit, but what happens if we equated these two? Sorry, what happens if we equated if we equated the two constants here? By these two, I mean c and c prime. They are not equal to each other. We don't know what they are, but we know that we can put bounds on them. And even though they are different from one another and the bounds are different, they're not that different. So let's go ahead and cheat a little bit, and let's say that c and c prime are equal to each other. If we equate then c and c prime, then what we get c prime equals to 4n squared times a minus a 2n, and c is equal to n squared times a minus a n. And so if we equate c and c prime, then what we get is 4 a minus a 2n is equal to a minus a n. And note, again, I just want to make it clear, this is not really true. These two are not actually equal. So this is cheating a little bit, like I said. But let's see where this takes us, okay? So what this means is that if we could actually set this equal, then that means the area, the true area, is equal to, if we work out the math, 1/3 times the quantity 4 area 2n minus area n. Again, this is not exact because c and c prime are not actually equal to each other. But what this does is this particular method actually drastically reduces the error, and this method is called Romberg integration. What do we just do here? Okay. This is the trapezoidal rule trap Z, with n subintervals. That's what AN is. A2n is trap Z with 2n subintervals. So if we have 2n subintervals, and we use trapezoidal rule to get some approximation of the area, and then we combine every other subinterval together to reduce the number of subintervals from 2n to n, we can do trapezoidal rule again, and now we have two different trapezoidal rule estimations of the area. If we combine these two estimations in just the right way, we actually get a very, very, very good approximation of the integral under the curve. And again, it is still an approximation because c is not equal to c prime. These two constants, these two bounded constants, here, c and c prime, that are bounding our error, they're not equal. So we're not actually setting the error equal to 0, but we are drastically reducing it. So in other words, what we want to do here for Romberg integration is we have 2n plus 1 number of points. In other words, we have an odd number of points, or a even number of subintervals. Then we're going to calculate two trapezoidal rules. So the first trapezoidal rule, which I'm calling area 0 here, is equal to the sum of I even up to 2n of the trapezoidal rule, 1/2 f of xi plus f of xi minus 2 times the interval xi minus xi minus 2. So I starts at 2, you know, 2, 4, 6, 8, all the way up to 2n. Now it's important that that you have 2n, that 2n, it's an even number if n is any integer, right? So it's important that you have an even number of points, or of subintervals here. And then area 1 is equal to the sum I equals 1 to 2n. And now we're taking every single I, and that's 1/2 f of xi plus f of xi minus 1 times the interval xi minus 1. So just the normal trapezoidal rule, except for we're specifying here that we have 2n plus 1 points, or 2n subintervals. And then if we do that calculation, then an even better approximation of the integral, better than either of the two, a0 or a1, is equal to 1/3 times the quantity 4a1 minus a0. Again, that's what's known as Romberg integration. And it is a much more accurate form of integration.